We are going to study about quantum numbers and periodic patterns related to these quantum energy levels. Here, the spectrum we have studied in our previous lesson. Different elements have their different emission spectrum as seen in this image. In our previous lesson, these lines represent in the emission spectrum is due to the electron movement from higher energy level to lower energy level. Let's take this example of hydrogen. There are number of energy levels exist in the hydrogen atom. From third energy level to second energy level, electrons movement emit red color electromagnetic radiation, and this green color due to the transition of electron from fourth energy level to second energy level. And there are another two lines in the spectrum due to fourth and fifth energy level electrons moving to the second energy levels. So therefore, this is the only lines we can observe in the visible range for hydrogen atom. There are infinite lines, however, you can observe in the infrared and visible range and also the UV range. So therefore, this energy between two energy levels represent the energy of that electromagnetic radiation. Therefore, in this observation of this experiment, we can understand the energy of an electrons are in discrete value. That means it's a quantity wise, there are countable numbers of energies are exist, not the continuously exist in these electrons. There's a discrete values. So that is why we call there's a quantized energies. So therefore we have to give some number or a letter to represent these energy levels. So that is why we are studying about these quantum numbers and quantum energy levels. When you further study about this single line, you can observe there are two or more lines represent in a single uh, line due to the sub energy level existing this principal energy level. We call principal energy level means that is the energy levels we studied in previous lesson. So in a single energy level, it may have another sub energy level. That is why we can observe these kind of divisional lines in a single exclusion image. You can obtain 3 or even more lines due to these sub energy levels. Therefore, there may have another energy level of an atom. So if you are going to study more atoms, they may have another kind of energy levels. So therefore, in other hand, we can obtain magnetic energy levels. That means if it is the energy lines are separated again if you are applying a magnetic field. So that means a magnetic energy level also obtained. Therefore, there are several kind of energy levels in a single energy level can obtain. So this part we are studying in the quantum numbers. About quantum numbers, the word quantum is used to represent the minimum amount of any physical property. So this word is derived from the Latin word. The meaning is how much, and it reflects the fact that quantum models always involves something common in discrete amount, and normally it use some integer values. We are dealing with integer values. So here in the quantum numbers, where the electrons exist in an atom have four numbers. One is principal quantum number, next one angular quantum number, or we call azimuthal quantum number. It represents the sub energy levels, and magnetic quantum numbers represent the magnetic energy levels, and spin quantum number for spin energy levels of electrons. So still you don't have any idea about these other part rather than principal quantum numbers. Uh, let's discuss these four individually to understand more about these quantum numbers. When we are representing an electron in an atom, we can define their location and their all properties using these four quantum numbers. That is why we are using these quantum numbers to identify an electron, or the place, the energy level where an electron can exist. So let's discuss individual quantum numbers and let's study what are those represents. When you're talking about principal quantum numbers, uh, in principal quantum numbers, integer values used to specify the shell or energy level. Uh, the electron is in form from 1 to infinity. So therefore, infinite number of principal energy levels may exist, and therefore infinite number of principal quantum numbers may exist in a single atom. Here it describes how far away from the nuclei the electron shell or level under consideration is. For example, the higher numbers of n have higher probability to find an electron far away from the nuclei, and similarly the lower number is very closer to the nuclei, and therefore high probability to find a electron in close to the nuclei. And these are the images we can represent the probability uh, area or probability space which can find an electron of uh, different quantum numbers. For example, n is 1 means low, it's very near to the nuclei, and n is 3 means it's far away from nuclei. They may have to find an electron. Earlier, these principal quantum numbers are not exist, and this principal energy level mm, name as English letters. For example, the closest energy level called K, capital K, L, M, N, O, P, Q, like numeric letter values are used in earlier. However, now we are using 1 to infinity numbers to represent the principal quantum energy levels. So therefore, now the principal quantum numbers are used to identify the energy levels. When we are representing an electron in an atom, we can uh, define their location and their all properties using these four quantum numbers. That is why we are using these quantum numbers to identify an electron, or uh, the place, the energy level where an electron can exist. So let's discuss individual quantum numbers and let's study what are those uh, represents. Next one is azimuthal quantum numbers. Azimuthal quantum number or angular quantum number also we call to represent of the sub energy levels of atoms. So here there's a pattern to find out an azimuthal quantum number related to principal energy level. For example, if the n is 1, that means principal energy level is 1, we can find out one azimuthal quantum numbers. That means azimuthal energy levels only one. If there are two for quantum number for principal energy level, we can find out two sub energy levels. That means two azimuthal quantum numbers exist. And three, there are three azimuthal quantum numbers exist. Four, there are four. And further, we can say if the principal quantum number is n, the n number of azimuthal quantum numbers can be exist in an atom. Different azimuthal quantum numbers represent the shape of the orbital. That means different azimuthal quantum numbers L define the different shape of their electron can exist around the nuclei. So they have also a letter to represent these quantum numbers, quantum levels. For example, if the L is 0, we represent s orbitals. So that means letter is s to represent L is 0, and L1 the representing letter is P, and for 2 D, and 3 F, and 4 is G, H, I, J, K. We can go for different energy level, but it is not popular because no any electrons exist further f orbitals in natural elements in the ground level. So therefore this is enough, this 4 is enough to understand for azimuthal quantum numbers. Now let's study their shapes. Here in this graph it represents the probability function where the electron can find out around the nuclei with the distance. So with the distance their probability is changed. For one is means one is n, and s means L is equal 0. For that kind of energy levels, they may have this kind of probability to find out an electron around the nuclei. This is spherical shape and it goes to 2s. This shape is same but the size is different. This is 3s, that means size is higher but the shape of that orbital is spherical. This is same for L is 0. So therefore azimuthal quantum number is 0 means they have similar shape where an electron can find out around the nuclei. For L is for L is 0. So this is the shape for L is 0, and if the L is 1, their shape is changed to this kind of shape, and L is 2, that means d orbital can have different shape. This is for f orbital. This is a shape is totally different. So we can understand those shapes more about when you are talking about hybridization. Let's discuss this hybridization and the shapes of this orbital later. When we are representing an electron in an atom, we can define their location and their all properties using these four quantum numbers. That is why we are using these quantum numbers to identify an electron or a place, the energy level where an electron can exist. So let's discuss individual quantum numbers and let's study what are those represents. Next important quantum number is magnetic quantum numbers, represented by simple m. Here the third of set of quantum numbers are magnetic quantum numbers, and it means the how many orbitals there are a particular type of their orientation in space of a particular orbital, and only 2 electrons can fit in an one magnetic quantum number. That means one magnetic level there may have only 2 electrons. Here the number of magnetic quantum numbers per one angular level exist according to this pattern. If the L is 0, the number of magnetic quantum numbers is 1. For 0, there are only 1 magnetic quantum numbers. For L is 1, that means p orbital. For p orbital, number of magnetic quantum numbers count is 3, and L is 2. L is 2 means d orbital. In d orbital, number of magnetic quantum numbers may have 5. Similarly, L is 3, we can have 7 quantum numbers. So then we can go further, and you should know for L, any number of L azimuthal quantum number may have 2L plus 1 number of magnetic quantum numbers. So therefore, this pattern is very important to understand how many magnetic energy levels exist in a particular azimuthal quantum number. And let's go how we can number this magnetic quantum. Here these are the example. For s orbital, that means L is 0, only one magnetic quantum number exists. For p orbital, that means L is 1, 2L plus 1 is equal to 3. So therefore 3 is magnetic quantum numbers are exist. We are giving numbers to this one as -1, 0 and +1. The above one only 0 we have. For d orbitals, that means L is 2. How many magnetic quantum numbers can be exist? 5. How we can give these numbers? 0, -1, -2, and here +1, +2. Similarly, for f orbital, there are L is equal 3, and therefore the number of orbitals can exist 7. So this 7 we can give numbers from 0, -1, -2, -3, and +1, +2, and +3 like numbers. So those are the magnetic quantum numbers we have to consider. When we are representing an electron in an atom, we can define define their location and their all properties using these 4 quantum numbers. That is why we are using these quantum numbers to identify an electron or the place, the energy level where an electron can exist. So let's discuss individual quantum numbers and let's study what are those represents. Next important quantum number is spin quantum number. Because in the magnetic quantum number, there are two electrons exist in a one magnetic quantum number. That means magnetic energy level contains only two electrons. These two electrons exist in two spin quantum numbers. Those are the fourth of a set of quantum numbers, and this two electrons contains plus half or minus half as the quantum numbers we can give for these two electrons. So therefore spin quantum number contains only two, one is plus 1, other one is minus 1. In a particular magnetic energy level contains both plus 1, plus half and minus half electrons. When you are talking about spin quantum numbers, let's understand the Fleming's right hand rule. In the right hand rule, that means in this image, image A contains the left hand, not it's a right hand. When you thumb up, so that means the thumb side is go to the conventional current. That means positive charge go through this thumb side to upward. There may have other fingers. The rotating direction of these other fingers represent the magnetic field it generates. Similarly, electron flow represented by the left hand side, image B. If you are considering not the conventional current, if you are considering the electron current or electron movement, you can represent this law in your left hand. In thumb side, any electrons movement can generate, then can create a magnetic field in the direction of other fingers are moving. So therefore there's a magnetic field. If electron movement means there's a magnetic field there. So therefore two spin quantum numbers are created to cancel out each other, each magnetic field. Here this represent electron movement to two direction. Due to this movement of one electrons, it's like a magnet. It acts as a magnet and it can have a magnetic field like this. And if it is a rotation of other direction, the magnetic field is you can generate into the opposite side. So therefore the direction is different, means there are two opposite direction magnetic fields are created. Therefore it's like a temporary magnets. Electrons are some kind of electron clouds are some kind of temporary magnets. Therefore they may have opposite side of their magnetic fields. So therefore two spin quantum numbers contain these two opposite direction of their magnetic field. These two are given numerical value. One is plus half and for other one we are giving as minus half. When we are representing an electron in an atom, we can define their location and their all properties using these 4 quantum numbers. That is why we are using these quantum numbers to identify an electron or a place, the energy level where an electron can exist. So let's discuss individual quantum numbers and let's study what are those represents. When you are representing these two spin quantum numbers with one electron, represented by an arrow. So normally we can use one single side headed arrows, or you can say double side arrows to represent the electron in a particular area. And arrow represent two electrons which have two spin quantum numbers, and the box in the above image represent one orbital of an magnetic quantum numbers. Therefore, in a single magnetic energy level contains two electrons which has two different spin quantum numbers, plus half and minus half. This summarized data we can represent in this table for different principal energy levels contains how many angular quantum numbers and their magnetic quantum numbers you can represent by this table. For example, if there's a quantum number, principal quantum number is 1, there are 1 angular quantum numbers. This angular quantum number represented by 0, and in a 0 angular quantum number or azimuthal quantum number contains only one magnetic energy level. This represented by 0, and this one magnetic quantum number contains two spin quantum numbers. They may have plus half and minus half. Therefore, total number of electrons can exist in principal energy level 1 is 2. And next, let's go to the principal energy level 2. There are only two number of azimuthal quantum numbers can exist. These two is 0 and 1. For 0 quantum number, we may have only one magnetic energy levels we discussed as earlier, but in the azimuthal quantum number is 1, there are 3 magnetic energy levels. We are giving minus 1, 0 and plus 1 for these 3 number of magnetic energy levels. So each magnetic energy level contains 2 spin quantum numbers, plus half and minus half. Therefore, when you are considering the principal energy level 2, it contains now 8 number of electrons can exist in the second principal energy level. And third principal energy level, we discuss the number of azimuthal quantum numbers can exist 3. For 0 we discuss, and for 1 we discuss already when you are talking about the second principal energy levels. And this 2 or d angular quantum number or azimuthal quantum number contains 5 number of magnetic energy levels. Those 5s are minus 1 to minus 2 to plus 2. Each magnetic quantum number contains 2 spin quantum numbers, plus half and minus half. Therefore, total number of electrons can exist in the third principal energy level is 18. You can fill this blank part of this table from your knowledge. Now you know the patterns, and try to fill these numbers by yourself to study more. Especially this question mark part, you have to give letter based numbers, and you have to find out how many number of electrons can exist in the nth principal energy level. So that is very easy to find out. Now you know the patterns and the when you are talking for common energy levels. This is a periodic table of the element. Uh, this periodic table also prepared according to the pattern of the quantum numbers. Therefore, this mm, electron filling is the base for construction of this uh, periodic table. So let's study about the electron filling rules for these quantum levels. When you are considering a chemical symbol, we have mass number and atomic number. Atomic number means normally we are considering the number of protons represent the atomic number. It is similar to the number of electrons in ground state, and mass number is the number or the summation of number of protons and the number of neutrons. So therefore these are the symbol we are using in the periodic table. For filling rules for electron orbitals, we should know Aufbau Principle, Hund's rule and Pauli's exclusion principle to understand the electron filling to a ground stage of an element. When you are considering the Aufbau Principle, it teaches us what are the energy levels of sub energy levels in a order of according to the increment of energy. In a single atom contains different energy levels. S, that means L is 0, L is 1, L is 2 and L is 3, likewise. So therefore when I am drawing arrow lines where the energy increment represent. So therefore you can understand how their energy increase with their energy levels, sub energy levels. So therefore first electron fill to 1s orbital, next 2s, then 2p, 3s, 3p, and next not to the 3d, it's fill into 4s, next it is fill into 3d. So therefore that is the pattern of this electron are filling. 3s and next 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, and 5f, 6d, and next one is 7p. Now I remove this other part, and then you have an idea how those electrons are filling according to the sub energy levels. Another graphical representation of energy increment with the sub energy levels. This is a special part we have to consider, that 3D and 4S. The 3D energy level is higher than the 4s. Therefore, after 3p filling of electrons, next electrons filling to the 4s energy levels. For filling rules for electron orbitals, we should know Aufbau Principle, Hund's rule and Pauli's exclusion principle to understand the electron filling to a ground stage of an element. Filling rule is Pauli exclusion. Discuss in the quantum numbers, there are two spin quantum numbers in a one magnetic energy level. So therefore, each orbital can hold two electrons with opposite spins. So this opposite spins, how it feels according to the spin energy levels we discussed in the Pauli's exclusion principle. So that means it represents there are no any electrons exist in a similar spin in a one magnetic energy level. For filling rules for electron orbitals, we should know Aufbau Principle, Hund's rule and Pauli's exclusion principle to understand the electron filling to a ground stage of an element. Next important rule is Hund's rule. Electrons occupy equal energy orbitals so that a maximum number of unpaired electrons exist. For example, let's consider the empty bus seat rule. Within a sub energy levels, place one electron per orbital before pairing them. Let's take this example. Consider p orbital, that means there are three magnetic energy levels. Let's consider how these electrons are filling into this p or L is equal 1 energy level. This is one electron can exist and next electron can exist in this one and third one and fourth one likewise. And next method to fill these electrons are like this kind of pattern. First it filling in the single spin level. After filling of this all single part, next it start to fill the other spin side. So this first part is the wrong and the second one is the right filling method. That means first they are filling one direction in a particular single azimuthal energy level, every magnetic energy level filling by their one direction, and next they are go to other spin side. That is the method electrons can fill according to the Hund's rule. Actually, if you didn't get these all rules, you can understand when you are considering the examples of electron configuration writing. When you are writing this electron configuration for particular examples, you can understand how these rules are work. Let's first consider oxygen. How many electrons are exist in oxygen? The atomic number of oxygen is 8. That means there are 8 electrons in their ground stage. So these 8 electrons, how it feel? First, 1s orbital, single electron fill, and next one is fill. Next energy level is 2s. That means principal energy level is 2. Azimuthal energy quantum number is 1. No, it's 0. 0. And there are magnetic energy level only one exists, that is 0. And next spin energy level, this is plus half and this is minus half. That is the electrons filling in the fourth electrons. Now we have another 4 electrons, how it will fill. Next energy level is 2p, that means principal energy level is 2. Azimuthal energy level is 1 for p orbitals. There are 3 magnetic energy levels, minus 1, 0 and plus 1. And there are spin energy levels are there, plus half and minus half. First it will this plus half, next plus half and plus half, next it will to the minus half. So that is the orbital diagram you can find out for oxygen. So this is the electrons filling pattern for oxygen. So therefore you can write down this as a electronic configuration 1s2, because there are 2 electrons fill in the s orbital, 1s orbital, and 2 electrons fill in the 2s orbital, and 4 electrons are filling in the 2p orbitals. Therefore you can represent this electronic configuration like this. Now let's consider first few simple atoms, how it fills their electrons according to the filling rules. Hydrogen, only one, is over. Therefore you can write down as electronic configuration as 1s1. Helium contains 2 electrons. How it 2 electrons exist? In the 1s orbital. Therefore you can write down electronic configuration as 1s2. And lithium, there are 3 electrons. How it will? Like this. Therefore the electronic configuration is 1s2 and 2s1. Carbon, this is the electronic configuration. Therefore electronic configuration 1s2, 2s2 and 2p2. Those are the 6 electrons exist in carbon in the ground stage. Like the similar pattern, you can write down different elements in their ground stage, how electrons are filling to their energy levels, and then you should know how to write down the electronic configuration of these different elements. That is very important, how to write down. Now let's consider some kind of orbital contains a large number of electrons fill into this heavy elements. This sulfur is not a huge heavy element, but there are 16 electrons. Some considerably high number of electrons are exist in sulfur. So how it fill? The 16 electrons. 1s2, 2s2, 2p6, next 3s2, 3p4. Now these 16 electrons are over, finish. Those are the electronic configuration in sulfur. However, this blue color part, there are 6 electrons. We call this as valence electrons. So therefore we can write down these valence electrons separately, and other part 1s2, 2s2 and 2p6 is a electronic configuration of neon. So therefore we can write down this co-electron as the neon configuration. Therefore we can write down this shortened form for the sulfur is neon configuration plus 3s2 and 3p4. However, this valence electrons part is very important to write down. If you are writing down this, both way are correct. In the shortened configuration, it is easy to write. Next, let's study what are the major components important in this shorthand configurations. Let's take this example. This is electronic configuration of sodium. That means this neon means neon electronic configuration, and 3 means the third energy level, the principal energy level, and S and 1. S is represented by orbital shape and their azimuthal quantum number. This is represented by letter. However, the quantum number is 1, and this 1 represented by the 1 electron in the orbital. Therefore, only single electron exists in this s orbital. Those are the representing this shorthand configuration. These are the example of shorthand configurations for some kind of heavy elements. Therefore, please try to practice how to write down an electronic configuration of a particular element. First, ionization energy means the energy required to release the loosely bound electrons of an atom to infinite distance from the nuclei. So that means to take out an electron from an atom to outside. So that has also similar pattern with related to the electronic configuration. So therefore, this is the first 20 element, the pattern of the first ionization energy, and also you can write down up to 60. It is better to find out, you can refer some outside sources how this related to the this electronic configuration. So please refer that one, and I will ask some question from you in the exam how this pattern are related to the electronic configuration. Therefore, this pattern and the relationship between the electronic configuration should know. That is a reference you should from outside sources. Although these filling rules exist, there are some exceptional cases with where that not obey with the filling rule. There are small number of elements. For example, chromium. There are atomic number is 24. When you writing down electronic configuration, it should be like this in the screen according to the filling rule. However, the correct way of this chromium is not as this electronic configuration. Let's consider this due to the reason of the half filling orbital. For example, here there are 3D 3D4 is the electronic configuration represent. That means 4 electrons in 3D orbitals exist in here. However, this single orbital has alone. There are no electrons. Therefore, this is some kind of unstable form. However, if it is filling, this total 5 electrons are filled, means some kind of stable form. So therefore, 1 electron from this 4s orbital can take into this orbital, and this can fill. Therefore, this 4s orbital reduce one electron, and d orbitals can fill one electron more. Therefore, in chromium, the correct electronic configuration is the second one. It is not as the similar to the it is not obey the filling rules perfectly. Similarly, copper also have this kind of thing, and when it consider the 3d orbitals, this is the d9 configuration, d9. However, this d9 orbital, there are 9 electrons. That means it is remaining 1 electrons to fulfill the 3d orbitals. So therefore, that is some kind of stable form. Therefore, they can also take 1 electron from this 4s orbital to fill this 3d, and therefore 1s orbital, 4s orbital can donate 1 electron to 3d orbital. Then it will fully fill 3d orbitals exist. Now it is stable than the previous stage. Therefore, this is different cases. So there are several cases exist in the nature. These are the examples in transition metals, and also in the lanthanide and actinide series also exist this kind of exceptional electronic configurations. Thank you very much for your listening, and please do your assignments and what you should refer in outside sources, and do your quiz in next week related to this content numbers. Thank you very much. For filling rules for electron orbitals, we should know Aufbau Principle, Hund's rule, and Pauli's exclusive principle to understand the electron filling to a ground stage of an element.